Good evening, everyone. Now we'll start our fourth unit, which is all about the computational heat transfer and turbulence modeling. Today we are talking about the application of FVM in computational heat transfer. Then next class we will cover the one-dimensional, two-dimensional study and unsteady state diffusion equation. Then what is the stability analysis? What is the explicit implicit method? The introduction to the turbulence model, specifically Raynaud's model. So let's start with the first topic, application of finite volume method in computational heat transfer. So it is having extensive application in computational heat transfer. So FVM is one of the most versatile numerical method used in engineering for solving conservation laws, as you know, mass, momentum, and energy. So application in heat transfer and look at governing equations that form the backbone of this method. So application of FVM is widely applied in solving heat transfer problem across multiple domains. Some of them are mentioned in this particular PPT. So conduction heat transfer, so it is used to solve or to calculate the steady state transient temperature distribution in the solid material. For example, design of heat exchanger and or analyzing the thermal performance of turbine blades, right? So convection diffusion problem, then radiation and phase change problem and multi-physics coupling. These are the applications where we are utilizing the final volume method to solve those problems. Like in the convection diffusion problem, we are seeing the cooling of electronic devices, HVAC systems, and heat exchanger. Similarly, radiation heat transfer, so it is applied to solve radiative heat transfer in systems like solar thermal collectors or furnaces. In the case of phase change problems, applications includes simulating melting, solidifications, or boiling process such as ice melting, phase change material melting, right? So multiphysics coupling, which integrates with the computational fluid dynamics to solve coupled systems such as aerodynamic heating during spacecraft rendering or thermal mixing in reactors. Governing equations like equations conservation of energy, general heat transfer equations, as you know, dou by dou t, rho cpt plus nabla rho cp vt, which is equals to nabla k delta t plus source term st. So rho is density, cp is specific capacity, t is a temperature, v is a velocity vector, k is thermal conductivity, and st is source term. So how we are going for the discretization using finite volume method? So we will divide the domain into control volumes and conservation law is applied to each control volume. Take the example of 1D steady state conduction problem. So d by dx, k dt by dx plus source term, which is equals to 0. If we want to discretize it, we can say k Tp minus Tw upon delta Xw minus k Te minus Tp delta Xe plus source term delta X is equals to 0. So what is Tp, Tw, Te? Temperature at the center, neighboring control volumes, and what is delta XW, delta E? Control volume distance. Okay. So these are the part of discretization. Next is convection diffusion equation. So you can see dou rho phi by dou t plus nabla rho v phi is equals to nabla dot gamma. Gamma is a diffusion coefficient. Nabla phi plus source term. So discretize the equation for the scalar variable phi. If we go, then which we can write it AP. So this is a simple conversion of 2D equations, that how we are discretizing the above equation 2D domain into the scalar variable phi, that we are going to cover in the next class. So what are AP, AW, AE, AN, AS? These are the coefficients which depends on the material properties and flow conditions.